Hey guys, in today's video we're going to be covering algebraic linear expressions, and to do that we first have to cover like terms, or we need to figure out what like terms actually are. Well, like terms can be either algebraic terms, terms with variables in them, or just numbers on their own, which are called constant terms, like the 10 and the 3 here. Now, when we look at the 2x and the 5x, we can say that they are like terms because they share the same exact variable. They both are x terms, 2x and 5x. On the same note, 6y and 8y are also like terms because they have the same exact variable next to them, the y's. Now, the 10 and the 3 are just two numbers on their own. As I said before, they are called constant terms. Sometimes they're simply referred to as constants in algebra. And because they're just numbers on their own, they're also like terms, meaning you can combine them as well. Now, I also wanted to show you two other examples, which we're not going to cover that much in this video. We're going to try and keep it relatively simple with a single variable term. However, I wanted you to kind of know that a term like this, like 3xy, is a like term with 7xy because they have two exactly identical terms, variables next to them. Therefore, 3xy and 7xy are like terms. Okay, and you also can have like terms that have not just the same variable but also the same exponent. Now, I wanted to briefly cover this so you guys get an idea of how you can tell like terms when you're dealing with exponents as well. Now, in this case, these two are exactly like terms because not only the a is matching, but the exponent is also matching. Later on, we're going to refer to this as terms to the second power or terms to the second degree. So the degrees or the powers match as well. Now, I'm going to give you an example here. Let's say we say 4a to the second degree or the second power is not a like term with, let's say, 5a to the third degree. Even though the a's, the variables match, the power of 2 does not match with the power of 3. This is to the second degree, this is to the third degree, therefore they are not like terms. So if I were trying to add them, I wouldn't be able to. I would have to keep them as two separate terms. Similarly, if I have a term like 3xy and I had another term like 3xyz, even though these two are identical because this one has an additional variable included in this term, these two are no longer like terms because of that extra z. So to recap, like terms can be algebraic terms or constant terms. If we're dealing with algebraic terms, we have to make sure that the variables match exactly. In this case, even though the two variables match, because this term has a third variable, the z, this becomes a term that is not a like term to the 3xy. At the same time, even if you have the same variable, but the exponents, the powers, aka the degrees, don't match, then they are not like terms either, even though the variables are the same. Now, I wanted to point out that if we have 3xy, and let's say we have a term like 7yx, now these two are like terms, even though we switch places with the xy and the yx. They are like terms because they contain the same exact variables with the same power. They're all to the first power, so together they actually make second degree, but that's going to be on another lesson. Right now we know that these two are like terms because they have the same identical variables. Even though they're not in the same order, they are like terms. Okay, now let's go back and focus on the easier terms here. So we're going to concentrate mainly on algebraic terms with one variable as well as the constants here. Now, looking at the 2x and the 5x, Now, the number in front, that's referred to as the coefficient. Okay. Now, some people like to define the coefficient as the number telling you how many x's the term has. For example, this term has 2 x's, so you can actually split 2x into x plus x. Okay, this is the expanded form of 2x. Similarly, 5x can be split into x plus x plus x plus x plus x. All right, 5 different x's adding together. All right, so one way to think of the coefficient is the number telling you how many unknowns you have in this term. In this case, you have 2 x's that are unknown that have the same value. It's unknown, but it's the same value, and it's being added together. Now, there is another way you can think of the coefficient. All right, instead of writing it as repeated addition, the 2x, I can actually split the 2x into 2 times x. All right, 2 times x and x plus x are actually equivalent expressions. All right, and we can do a quick test here. For example, if we chose a value for x, let's say we made the x 6. All right, well, the 2 times x would become 2 times 6, whereas the x plus x would become 6 plus 6. 2 times 6 would give us 12, and 6 plus 6 is also 12. So as you guys can see, that 2 times x is actually equal to x plus x. They are equivalent expressions. All right, and if we wanted to try a different number, you will notice you're going to get the same result. So let's choose one more x, a different value for x. Let's use a slightly bigger number, I guess. Let's use 13. All right. So here it would be 2 times 13, whereas here it would be 13 plus 13. Well, 13 plus 13 will give us the 26, and 2 times 13 would also give us the 26. As you guys can see, 2 times x is equivalent to x plus x. And if I were to do the same thing with the 5x, meaning 5 times x, and I made it equal to x plus x plus x plus x 5 times, adding it, it would actually be equivalent. I'm not going to do that because it would take time because there are so many x's there. So I just wanted to understand that 5x is actually equal to x plus x plus x plus x plus x, but it's also equal to the 5 times the unknown value. In this case, the unknown value is our variable x. Okay, because of this, we can actually combine the 2x with the 5x even without knowing the value for x. Here's how that works. So I can split the 2x into x plus x, and let's say we're adding these two together now. And I can also split the 5x into the 5x's, which is x plus x plus x plus x plus x. All right, and if I were to add them together, well, let's count the x's. How many x's do I get here? I'm gonna get 7 x's. All right, 2 from the 2x and 5 from the 5x. So we got the 7x. You can actually skip this middle step, the expanding form, and you can actually get to the answer right away. So we can simply say that x plus x plus x plus x with all those x's is simply going to give us the 7x. So in order to save time, we do not need to write the expanded form. We simply are going to add the coefficients because 2 plus 5 would give us the same result. All right, so here the 6y and the 8y, we can do the same thing. We can either expand it, but that's going to give us a bunch of y's adding together, or we can simply say, okay, we're going to keep the y because they are like terms, and we are going to add the coefficients, in this case the 6 with the 8, and when we add them together we're going to get the answer 14. So this will become 14y. Alright? Now constants, of course, or constant terms are regular numbers, so we all know that you can actually add them and subtract them. So if I add these two together, I'm going to get 13. And similarly, if I were to subtract them, I'm going to get the 7. All right. Here, the result would be very similar to the process that we did here. We're going to add the 3 with the 7 to give us the 10. And because they have identical variables, this would be 10xy. Or 10 times x times y if you write it into a multiplication expanded form. All right. And for the last one, same idea. When we add them, you keep the same variable term. In this case, it's not just the a, but it's the a to the second power or second degree. And then you are simply going to add the 4 with the 2, and that will give you the 6. All right. Now, as I mentioned before, we're going to focus only on the simpler terms, either one variable on the term or regular constant numbers. So let's move on to our next slide here. Now let's look at an actual algebraic expression. Now here you've got multiple terms. Now before you start to simplify the different terms, or simplify the expression, I should say, what we first have to figure out is if there are any like terms in that expression. If there are, then you can simplify it. If these terms were all different terms, not like terms, you would have to leave it as is. In this case, we can see that 7a and 2a are like terms, and 8 and 2 are also like terms. They are constant terms. So here we would add the 7a with the 2a because you have addition in the middle, and you would get the 9a. And then here you would add the 8 with the 2, giving you the 10. And because they're both positives and we're adding, you simply bring the addition sign to get the final simplified expression. Now, can we simplify this any further? Well, we ask ourselves, is 9a and 10, are they like terms? The answer is no, because this is an algebraic term, meaning a term with a variable, the a, and this is a constant term, a term that's a number without a variable. And because this is a constant term, this is an algebraic term, they cannot combine. All right, now looking at this one, let's look at like terms. Well, we got 9d. Do we have any other term that has the d variable? We do. The 4d has it. Now, the 4g is not a like term with the 4d because the variables are different. However, the 4g and the 2g are like terms because they both have the variable g. Okay, so here, now instead of adding like we did here because we had addition, here the like terms will be combined by subtraction. So here we would do the 9 minus 4, which would give us the 5. And because they're both algebraic terms with the d variable, it would be 5d. Here we subtracted the 9 with the 4 to get the 5, and we kept the variable d. Now we go ahead and do the next two terms, the 4g minus the 2g. Again, this is another subtraction, so 4 minus the 2 would give us the 2g. All right, now because the 4 is a positive, and when you subtract it, the result answer is a positive, so it will stay as addition. All right, now here we got the 5d and the 2g. Are they like terms? Can we combine them? The answer is no, because this has the variable d, this has the variable g. They are not like terms, so this is the simplest form for this expression. Now I'm going to quickly write another expression here. Let's say 7x plus 3y plus 5. Can we simplify this expression? Well, let's look. Do we have any like terms here? We got the x here, In the middle term we have the y, and the last term is just a constant term, meaning a regular number with no variables. So therefore we do not have any terms that match, therefore we do not have any like terms. In this case, this is the simplest form for this expression. So if you had a question asking you to simplify this, well, the answer would be, this is it. This is the final answer. It cannot be simplified any further than that. In order to simplify algebraic expressions, you need to have like terms that can combine either by adding or subtracting them. Now, these two examples were very easy, pretty straightforward. Now I'm going to show you when things get a little bit more complicated. Looking at these two expressions, we do the same process. We start looking for like terms to simplify. Now, do we have any like terms? Yes, we do. We have the 9w here and the w here. And we also have the 13 over here and the 5 over here. So we got two algebraic terms with the same variable and two constant terms, the 13 and the 5. Now, here's the problem. They are not next to each other. 9w is over here, then you have the 13 in the middle, and then you have the w afterwards. So the question is, how will I combine them? Will I be adding the 9w with the w, or should I subtract them? How do we do that? Well, this is where we gotta learn about the next property. So before I simplify, or before I show you how to simplify this, I wanted to talk to you a little bit about the commutative property. Okay, now simply put, the commutative property allows you to swap the numbers or the terms in an expression. For example, 6 plus 3, if we swap places and we get 3 plus 6, in both cases we can say that they are going to be equal to 9. All right? And because you could swap the 3 and the 6 without changing the answer in the end, we say that addition contains, or you can use the commutative property with addition. Okay? That operation is possible with the commutative property. Now we can try the same thing with multiplication. We can swap the 3 with the 6. We can make it 3 times 6. And then we'll notice that 6 times 3 or 3 times 6 will give us the same answer. In this case, it's the 18. All right? Now, when we look at the subtraction and division, things are not the same. Now, if we subtract 6 with the 3, we get 3. All right? But if we swap places and we do 3 minus 6, because the 6 is the greater absolute value from the 3 and you subtract it, your answer is not going to be a positive 3. It's actually going to be a negative 3. All right? So as you can see, if you swap places with subtraction, you will not get the same answer. Similarly, if we do 6 divided by 3, in this case we're going to get 2. Now if I swap places, 3 divided by 6, well, in that case you will get 0.5, which if you write it as a fraction, it would be half, or 1 over 2. So clearly these two are not the same. So subtraction and division cannot, you cannot perform the commutative property with subtraction and division. You can, however, do it with addition and multiplication. Now this is crucial because when simplifying terms, we need to move things around, and the commutative property enables you to swap things, to move things around. So addition is quite easy to do. Multiplication is as well, however, in simplifying like terms, you're dealing more with addition than the multiplication aspect of the expression. Now, what can we do when we're dealing with subtraction? Well, there is actually a trick. And here's the trick. Technically, it's not a trick. It's a property that we can use. Now, when we say 6 minus 3, we are technically saying positive 6 minus positive 3. So both the 6 here and the 3 are positive numbers. The subtraction is the operation. So you are subtracting a positive 6 with a positive 3 to give us the answer, which is 3. Now, if we keep the 6 the same, we keep it as positive 6 here, what we could do is we could swap the subtraction with the addition. So, and I should say the subtraction with the positive, we can swap them. And we can make, instead of having it as subtraction, we can make this operation addition. And that minus will become the negative value of the 3, okay? If we do this, and we add a positive 6 with a negative 3, we actually end up getting the same result. That is a positive 3. What this shows us, or what this tells us, is that subtracting a positive is the same as adding a negative. Now, why is this useful? Well, it is useful because when you're subtracting, you cannot swap the 6 with a 3. However, because we can turn a subtraction into an addition problem, or task, I should say, what we can do then is we can swap them. So in this case that I turn this into addition, I can actually now move the 3 over and the 6 over. However, when I move the 3 over, I need to move it as now the new term, which is the negative 3. The 6 didn't change, so you just move it as is while keeping the addition in the middle. So, if we wanted to move things around and you had a subtraction, you need to change that subtraction into addition, making the number from a positive, in this case, to a negative. And when you move it, you don't move it as a positive term, you're going to move it as a negative term. All right? And if we do the math here, negative 3 plus 6, you actually get a positive 3. And we can do a little test here. Let's see. So here I'm going to draw a quick number line. Now, number line is quite useful because it shows us, it visualizes how addition and subtraction works with negative and positive numbers. So I'm going to bring it here. Now, in our first case, we had 6. Now, because I know I'm going to subtract, I'm going to make the positive 6 over here. And then if I subtract 3 from the 6, I'm moving towards the negatives, which is to the left side. So the negatives are to the left of the number line, positives are to the right. So if I subtract 3 from 6, I started the 6, and I got to move 3 units that way. So the first one would be the 5, the next one would be the 4, and the third one would be the 3. So 3 units, 1, 2, 3. So this is the equivalent of taking away or subtracting 3 from the 6. You end up at the 3, and that's your answer over here. Now, similarly, when you're adding a negative, it actually is doing the same thing. You're starting at the 6, and you add a negative. Now, because you're adding a negative, even though it's addition, it's telling you to go or lose 3 values, go towards the negatives 3 times. So you end up going in the same place, which is to the left. So you end up with the same answer. Now, if we do this version over here, let's see, I'm going to have to make another number line here. Let's see if I can fit it at the bottom really quickly. So I'm going to do it, I guess I could do it down here. All right, now let's see. We're going to start at the negative 3. So I'm going to put the negative 3 on this side because negatives are to the left of the number line. And I know that I'm adding 6, so I'm going to go towards the positives. All right, so negative 3. Now, plus 6 from negative 3 means I got to move 6 units, but instead of going left with the 2 negatives, now with a plus 6, I actually have to go to the right towards the positive 6 units. So the negative 3 would be the first one, or where we start, I should say. The first one is the negative 2 after 3, then it's negative 1, then it's the 0, then it's the 1, the 2, and then finally the 3 here. So starting at the, let's use purple, starting at the -3, I gotta move 6 units. 1, 2, 3, 4, 5, 6 units to the right. So I'm adding 6 units to the -3. I end up at the answer, which is 3. So what I'm showing you guys here is that you can swap numbers even if you have subtraction. However, you need to treat that subtraction not as a regular subtraction, but as a negative value. So you need to think of this -3 as a -3 if you swap it over. All right? So with this in mind, let's take a look at the previous expression. Here we've got 9w plus 13 minus w plus 5. Now I'm going to do it first without thinking about the commutative property. What I'm going to try and do is I'm going to put the like terms together. So I want to put the w's together and the numbers 13 and 5 together. This is one way of simplifying, by moving like terms together. So if I were to simply bring down the 9w, and now I want to swap the w with the 13, so let's say I did plus w here, and then I moved over the 13, so the 13 would become, has the subtraction here, minus 13, and then plus the 5 did not change. So in this version, what I'm doing is I'm swapping the w with 13 without changing any of the operations. I kept this as addition, I kept the middle operation as subtraction, and I kept this as addition. I simply swapped the w with 13. At first glance, this looks like a normal, okay move. Here's the problem though. Because subtraction does not allow for the commutative property to be performed, you cannot simply swap this w because it has the subtraction. What we first have to do is we first have to treat or change this subtraction into an addition. So what I'm going to do here really quickly, let's see if we can make this, nope. I'm going to go over here. So what I'm going to do is I'm going to change the subtraction into addition, and I'm going to make the w a negative. So I swapped the signs, changed the subtraction to addition, and I made the positive w into a negative. So now when I swap it, I'm not going to swap it as a positive w, but I'm going to swap it as a negative w. So the final result will be the 9w, I guess you can say plus here, negative w with parentheses. Now the 13, because the 13 had the plus sign here, and this became a plus, when you move it over, it stays plus. Okay? And the 5 I didn't change, so that stays as positive 5. Now I used green here, so let's underline the like terms. We got the w terms together here, and you got the constant terms together here. So now we combine. Now one thing I want to bring up here, when you combine, this w doesn't have a numerical coefficient here. We can actually put 1. Anytime a variable doesn't have one, you can put a 1 there. Okay, this is the equivalent of a 1w. So when we combine the 9w with the negative 1w, you know you have to deal with that 1 value. All right, now again, here you got a positive 9 plus a negative 1. That is actually not going to be adding, but it's going to be taking away 1 from the 9 because you're going towards the negatives by 1 unit. So this becomes 8w. All right, now the 13 and the 5 here, because they both are positives and they have the addition signs, they will give you, they will add, giving you the answer, which in this case will be 18. All right, now the way I showed it, it was quite complicated because I wanted to bring up the point that you cannot simply swap when you have a subtraction sign. You got to change it to addition, carrying that minus or a subtraction and make it into a negative before you move the w. There is, I guess, a simpler way to look at this. So what I'm going to do instead, let me erase this really quickly. I'm going to leave the answer at the bottom here. All right, so here's what I'm going to do. Instead of changing this to addition and putting the negative next to w, what I'm going to do is I'm going to look at this expression as separate terms. All right, so the 9w here, it's clearly going to be just regular 9w. All right. Now the 13, again, it's 13. Now, when you look at it as a single term, you gotta, I like to circle the operation in front of it. So you can think of this no longer as an addition sign, but as a positive 13, which makes the next term, the w term, a negative w. So what I'm doing now is I'm looking at the expression as separate terms. So this is a positive 9w because it does not have a sign in front. This is a positive 13 because of the addition and there's no other minuses there. The w now will be acting as a negative w in this case, and the 5 is a positive 5 because it has addition and no other sign. So now when I swap things, I'm going to swap them with the operation. So when I move the w next to the 9w, I'm going to, well, first the 9w stays the same because it was in the front, but when I place the w next to it, I'm going to place it not with an addition, but with the sign in front of it, in this case, the subtraction. All right, and I can put a 1 there just to remind myself that I'm actually going to subtract the coefficient of 9 with this coefficient, which is a 1 in this case, to give me that 8. Similarly, I see that 13 has addition, so I simply move it over with the addition, 13, next to the plus 5 that has addition. By doing it this way, by putting squares, or you can even do all oval shapes, whichever you prefer, and moving them with the operation, you are keeping track of the actual value for each term. All right, so when you end up combining them, 9w minus 1w here will give you the 8w here, and the 13 plus 5 will give you the 18 here. All right, so using this strategy, I'm going to start with the 8x, and I'm going to look for another x term. Now, the sign, the plus, belongs to the term that comes after it. So the plus belongs to the 5y, the minus belongs to the 7x, and this minus belongs to the 2y. So I'm going to put a little rectangle around 5y, keeping the plus with it. Another rectangle over the 7x, keeping the minus around it, and the 2y, keeping the minus. Now, the 8x will combine with the 7x, and the 5y will be combining with the 2y. So I can do two things. I can do the operations on the spot and write the final answer here, or I can move them next to each other. What I'm going to do in this case to make it a little quicker for ourselves is I'm simply going to do the operation as is. So 8x minus 7x. Well, that's subtracting 8 with a 7, so that should give me an answer right away, which is 1x. All right, because 8 minus 7 is 1, bringing the x down. And then here I do 5y, which is a positive, so it's positive 5y minus 2y. Well, that's easy enough. That's going to give us 3y. Now, because the 5 is the greater absolute value and it's positive, when you subtract it with the 2, it gives you a positive answer. So that positive answer allows us to have an addition sign here. All right. Now, is this the simplest form? Technically, it is not, because of this 1 in the front. The 1 is no longer needed. Once you combine the like terms, you no longer need that 1, because 1 times x is simply going to give us x. So the simplified version would be x plus 3y. And this is why when you see variables that are alone, you never see them with a 1 in front, because they are simplified into the simplest form, leaving it as just the term without any coefficient. But in reality, it has a coefficient. It's the 1. You just don't need it there because it doesn't do anything to the x when you multiply it. All right, so let's go ahead and move on to our next slide. Now this will be a little trickier because we're putting in more terms and also a lot more negatives and subtraction. So here we gotta be comfortable with integers, adding and subtracting integers. And if you struggle a little bit with that, I would recommend using the number line. I'm gonna show you how to use the number line for this scenario, but once you get an idea of how to do it, you can technically visualize it in your head without actually using the number line, without actually having to do the number line, because that takes time. So first thing we're going to do, now I'm going to try and use the rectangle method, circling the term, or I should say putting squares around the terms. I'm going to try and color code it. So I'm going to put the rectangle around negative 8z, and now I'm going to look for another z term. It is right over here. Now if I were to put a rectangle around it, I gotta make sure that I take that minus in front of the z as well, because that will become the value of z. So you can think of this as a negative z. All right, and then I can do the same thing with the constants here, which is the plus 7, which is a positive 7, and the minus 13 here. All right, and then I do not necessarily need to put the like terms next to each other, although you can. Now what I do recommend in this case is, because the z does not have a number coefficient in front of it, remember we can always put a 1, so that when we do the math we know we have a negative 8 minus 1. Now to do the math here, as I said, I'm going to quickly use the number line to guide us a little bit with this. So let's see. Okay, so here's the number line. Now to do it, I'm going to start with a negative 8. So in this case, the negative 8, I'm going to subtract 1. So I started the negative 8. In this case, I can do it anywhere because I'm only subtracting 1 from it. Now, if you subtract 1 from the negative 8, when you subtract, you always go to the left towards the negative. If you add, you go towards the positives. However, if you're adding with a positive number, not with a negative, if you're adding with a negative, it still goes towards the negative. So in this case, we are subtracting. Now, if you think of this as a subtraction, then the 1 technically is a positive. If you think of this as a negative 1, then you're technically going to be thinking of this as negative 8 plus a negative 1. So depending on how you think of this minus will change the way you verbalize this operation. So now we can say that we are doing negative 8 minus 1, or subtracted by a positive 1. In that case, again, you got to take away 1 from the 8, moving you once to the left. So to the left of negative 8, you have negative 9. We're going further towards the negatives. So the answer here would be a negative 9z, because they're both z terms. Now when we do the numbers here, the 7 minus 13, you can think of this as 7 take away positive 13, or 7 plus a negative 13. Either way, you're going to take away 13 from the positive 7, minus 6. All right, and that's our final answer. So because things get trickier, I'm not going to be using the number line for this expression. I am simply going to do this mentally. Let's go ahead and put the rectangles around the like terms here. I'm going to put one over the negative 2x. And then I look for another x term. There is one all the way over here, the 11x. Now the 11x has a minus, so I've got to make sure that I include that as well here. All right, so I got those two. Then I can go to the 14y. Now the 14y has a minus in front of it, so I got to make sure I include that as part of the rectangle. And then I look for another y term. There is one over here, the 7y. Now the 7y has a minus in front of it, so I'm going to encompass that. Now the 5 here, it's a constant term, and as you can see, there is no other like term for the 5. let's use the black color here. So the 5 will be on its own. The 5, I'm going to put it all the way in the back, and there is a reason why you put constants in the back usually. It's because they have the lowest degree, meaning they have actually 0 degrees, but I will explain that in a later video. So right now I'm going to start with the x term since I see the 2x first. Now here I'm going to be combining the negative 2x minus 11x. Now if you combine these two and you do the math, we're actually going to get a negative 13x. The reason why you're going to get a 13 or a negative 13 is because we're starting at the negative 2 in the number line and we're taking away 11 more. So you're moving 11 more into the negatives. So if you move 11 more units from the negative 2 into the negatives, you end up at negative 13. Now let's do it with the y terms. Here you have 14y, and it's a negative 14y because it has the minus in front. So it's negative 14y minus 7y. Well, let's think about it. If you started in the number line in the negative 14 and you're taking away 7 more, you're going to go further into the negatives. So if you combine the negative 14 with a negative 7, you end up with negative 21y. All right? And then the 5, that's all alone. I didn't do anything to the 5. We did not combine it with anything. So I simply am going to bring it in the back. And because it's positive with a plus, that's just plus 5. All right. Now, once you write the terms, that negative now, when you have it in an expression, now will behave as a subtraction. So one way to think of the minus signs or the addition signs is you think of it as a negative if you're looking at it as just the term, or you think of it as a subtraction if you're looking at the entire expression. So this minus 21y, we can think of it as subtraction by 21y if you're looking at the whole term, or simply a negative 21y if you're just focusing on the term itself. So that's one way of differentiating between a negative and a subtraction, although technically they do the same thing. And with that, I'm going to conclude the lesson here. Please make sure to like and subscribe. Also, please feel free to comment with any suggestions or any ideas about any of the future videos. And if you think I can do something different to make this even more understandable for you guys, please let me know. Thank you so much and have a good day. Bye.